Okay, so we would like to compute the vector surface integral of the vector field x, y, 3z over a cylinder which starts at height 0 and terminates at height 5. And it's really part of the unit cylinder, which is centered around the z-axis. So the radius is 1 here, and we go from z equals 0 to z equals 5. And we also know that this is oriented with the outward normal. So this is S. Okay, and as usual, we need to begin by finding the normal vector for this for a parameterization. And we're going to use a very interesting parameterization here. So the idea is pretty simple. Think of it this way. If I write down r cosine theta, r sine theta, and z, these are the expressions of the Cartesian coordinates with respect to cylindrical coordinates. So if we actually restrict r to b1, then we find ourselves exactly on the surface of this cylinder. So if I erase this, and so by varying theta and z conveniently, and where should that be? So theta should be between 0 and 2 pi. Again, we have the usual situation where whatever we get for 2 pi is the same thing that we get for 0, but since we're talking about integration here, and that's a part of the domain that has 0 area, there's no problem with its contribution. And z should be from 0 to 5. And so if I put this together into a vector that I conveniently denote by g of theta comma z, which is unusual. Usually I take other letters like u and v for the parameterization, but here I just want to really suggest that what we're doing has to do with the cylindrical coordinates. And we saw in a previous example a parameterization of a sphere using again using a vector valued function that is inspired by spherical coordinates. So it's pretty much a very similar situation here. Okay, let's take the normal vector. So this will be g sub theta cross g sub z. And this is negative sine theta cosine theta comma 0 cross with 0, 0, 1. And this will give I, j, k, negative sine theta cosine theta 0, 0, 0, 1. And we delete the first row, the first column, and we get cosine theta. We delete the first row, the second column, we will get negative sine theta, but that's the middle term. So we put an extra negative sign that gives us sine theta. And finally, the other one is 0. And now here comes the interesting question. Is this the right vector? How can we possibly find whether it's the right vector or not? And the idea is actually pretty simple. Take a specific point, like this one. This one corresponds to what? At this point, theta is 0 and z is equal to 0. right? That's how we obtain that point. It's in Cartesian coordinates, that's the point 1, 0, 0. And test to see what you get for this normal vector at that point, and check to see if it satisfies the if it's compatible with the chosen orientation. If it is, you keep it. If it's not, you just multiply by -1. So if we set theta equals 0, what vector do we get? We get the vector 1, 0, 0. And ask yourselves, what is, let me change color here so that you can see it a little better. What is the vector 1, 0, 0? And the vector 1, 0, 0 at this point, if we sketched at that point, points like that. And that's certainly outward, which means that we got the right orientation. So there's no need to adjust here. And so we can proceed with the pullback of the vector field onto the domain of the parameterization. So simply speaking, the composite. And if we go back to the formula for the vector field, we will see that this tells us that wherever we see an x, we should replace it by cosine theta. Whenever we see a y, we should replace it by sine theta, and wherever we see a z, we should just leave it as it is. So this is f of cosine theta, sine theta, comma z, and this is going to be cosine theta, sine theta, 3z. Okay, and now we take the dot product. And we simplify. This is very agreeable. But you will see that eventually in many of these examples, the challenge is to get everything set up correctly. Once you get everything set up correctly, you may have pleasant surprises like this one, where the integrand ends up being the simplest function in the world, the function 1. So what we need to do eventually is just integrate this over the domain of the parameterization. And of course, what we get is the area of the rectangle. So we will get 2 pi times 5, which is equal to 10 pi. And this completes our exercise. Thanks for watching.